So yeah, I'm going to talk about time-dependent microstate geometries in ADS3. This is mainly based on those papers. So the first three with Bogdan Gantchev, Stefano Giusto, and Rodolfo and Nick. Actually, Rodolfo talked about those papers already, but in the context of the supersymmetric solutions that we've found. And now I'm going to talk about them for the non-supersymmetric solutions. And I'm going also to focus on this last paper, which is about time-dependent solutions. All right, so let me start with some background and some motivation. The overarching goal here is to understand the microstates of black holes. So consider a black hole in GR is given by this sort of geometry. We know we can solve the Einstein's equations, and there's only one solution. But we also know that the black hole has an entropy, which is proportional to its area, to the area of the horizon. And we want to know where the microstates are, because they are not in GR. In string theory, we know that we can find those microstates, but only at zero coupling. This is what Somenja and Waffer have shown. And now we want to understand what those microstates look like at strong coupling. And what I want to argue, and this is the motto of the fuzzball program and the microstate geometry program, is that actually the microstates do not look like the standard GR solution. You would already expect that in a theory of quantum gravity, the singularity of the horizon should be resolved somehow. But actually, we want to go further and say that even the event horizon must disappear from the solution. The reason for this is the paradox of information. We know that horizons are problematic once you want to include quantum mechanics in a theory of gravity. And we know from the small corrections theorem of Mathur that if we want to preserve unitarity and locality, then having a horizon in a vacuum is a problem. And we need to have structure at the scale of the horizon. Now, adding structure at the scale of the horizon is not an easy task. Must matter if you put them at if you try to put structure here, well, it will fall into the singularity. Even if you manage to use some kind of pressure or anything to maintain structure here, well, you don't want only to put structure. You also want that this structure is stable when you change the gravitational coupling. But when you increase the coupling, the gravity is attractive, so matter tends to fall. Whereas black holes tend to grow, and so if you increase the coupling, stuff will fall into the black hole. So we need something else, and this something else can be, for example, the non-perturbative degrees of freedom of string theory. And in particular, there are Brains's bound states that we can use. Brains's, their particularity is that their mass decreases when you increase the coupling, the gravitational coupling. And that means that if you consider this kind of bound states and you increase the coupling, the size of these bound states will actually increase, not decrease like standard matter. And it will increase at exactly the same rate as the size of the black hole increases. So this leads to the fuzzball conjecture that there are exponential S such string or brane bound states that are very, very stringy, very quantum, very hard to describe, but they fill out the full phase space of black holes. And so this kind of geometry do not exist in the quantum gravity. Here you can imagine that the Wilby horizon will be somewhere here, and the size of these fuzzballs is the size of the horizon. Now these things are very complicated to describe, so we want to simplify the problem, and we can look at coherent excitations of fuzzballs. And what we obtain is microstate geometries. The microstate geometries can be described within supergravity, and the geometry looks kind of like this. So asymptotically, it looks exactly like a black hole, but you see that instead of having an event horizon, we get a smooth cap, and we can construct a lot of geometries like this. So how do we do that? Well, one of the ways to do it is to use supersymmetry. We know that supersymmetric solutions are much simpler to construct, and indeed there are a lot of solutions that have been built like this. The most important family of such solution is the superstrata. It's been built nearly a decade ago. And there's been many successes with those solutions and other supersymmetric solutions. So I didn't dare try to list everyone involved in this, so I will refer you to the previous talks that we had. But all the successes we can name, for example, the precision holography, like Rodolfo was telling us about, and David. And we can also probe those geometries. We can see the appearance of tidal scrambling, of trapping of matter. And then there's the question of the observations and imaging of the geometries, what they would look like in the sky. But all of this is supersymmetric. And at the end of the day, what we want to really understand is this object. We want to understand the microsite geometries of black holes in the sky, and they are not supersymmetric. So a lot of the properties of supersymmetric black holes translate to the non-supersymmetric case, but some of them don't. And for example, what we want to understand is the dynamics of black holes, of the microsite geometries, and the equivalent of the Hawking radiation. And this is not something we can do with supersymmetric solutions. So it's much harder to find and to build non-BPS solutions, but still there has been some progress that has been made over the years. The first such solution is a JMAT that we've already heard about in this conference, and its generalization. And there have also been some running ball solutions, and tomorrow Pierre is going to tell us about his short-shelled microsites. But today I want to tell you about microstrata. And microstrata, you can understand them as some kind of non-BPS generalization of superstrata. I will tell you exactly in what sense a bit later. And in particular, in this talk, I want to talk about how to build time-dependent microstrata. And this is important because first, we can explore a much bigger phase space when you look at time-dependent solutions compared to time-independent ones. And also, we can start to understand the dynamics of non-BPS microsites. It's only in ADS3, but maybe it can teach us something about how those microsites will work in flat space. All right, so let me tell you how we can construct microstrata. The setup is the D1, D5 system. You take type 2B string theory, you compactify it on a 4 torus and on a circle, and the circle is understood to be much bigger than the torus. And you put on this, you put there a bound state of D1 and D5 branes. The D5 branes wrap all the directions, all the compact directions, and the D1 wrap the Y circle. And when you consider this system and you look at it in supergravity, you can compute it by reaction, and you find that what you obtain is global ADS3 times S3 times T4. So this is the ground state of the theory. Now you can add excitations, for example, momentum waves, and you get deformations of the geometry when you back react. This whole system is dual to a two-dimensional CFT. It's already been said several times in this conference. The CFT is a standard symmetrical bifold model with a central charge proportional to the product of the number of branes. So now we want to build non-BPS states in this theory. We will focus first on a single mode superstrata. Rodolfo explained to us what the superstrata modes looked like in the CFT. And this is only a single set corresponding to the perturbation of a superstrata, a light operator. The light operators look like this. So we have a chiral primary of dimensions half and half, and then we act on it with a Virasoro generator a certain number of times. Now we want to construct non-BPS states that generalize this superstrata, and the way to do it is to add right-moving excitations. And there are essentially two nice ways we can do that. The first way is to use the right-moving generators. We can add a certain number of powers of the right-moving generators, and then this state, this copy, will preserve no supersymmetry. There's another more subtle way to do it, is to consider two different constituents in two different copies of the symmetrical bifold. Each copy individually here and here would preserve some amount of supersymmetry, but they preserve different supersymmetries. And so when we put them together in a heavy state, they will preserve no supersymmetry at all. So you can see that here the state is grayed out. This is because I'm not going to focus on them today. I talked about them last year. And today I will focus on those ones because those are the ones that I will then that I will then explain how to construct time-dependent solutions out of them. And here I want to say also that there's another kind of states that is not directly it does not directly come from the original superstrata, but it can be built the same way. And they look like this. Here now the chiral primary is of dimensions 1 and 1. The objective is to construct the dual to these states in the bulk and find their back reaction in the bulk. And as Rodolfo also already told a bit before, we want to use a consistent truncation to do that. The reason is that in 6D, well, we have trying to find to solve the equations of motion directly in 6 dimensions would be way too complicated. And so we can look at a certain constant truncation that has been found by Daniel, Robert, and Nick a few years ago. And in this theory, this theory contains all the 10n superstrata. So, thank you. This theory contains all the 10n superstrata, and also, as we will see, it contains it can be used to describe these generalizations. So it works like this. In 6 dimensions, we have an ADS 3 times S3 asymptotic. So the solutions are asymptotic to ADS 3 times S3. And we will impose a restricted set of modes on the sphere. So you see the sphere part of the geometry is very, very simple. It's only encoded by this matrix of scalar M, and these gauge fields here that fix the vibration of the S3 on the ADS3. So to visualize a bit the fields of this theory, here we have a 3-dimensional metric that is asymptotic to ADS3. Then we have this matrix M, a symmetric matrix of shape modes of the sphere that deform the spheres sort of like this. And then we have a matrix of gauge fields that describe how the spheres fibered over the ADS3. In addition to that, we have non-geometric degrees of freedom. We have the scalars chi, which are the main momentum carrier, and that correspond to the B field and to the action and the axion. The whole theory has an SO4 gauge invariance from the isometries of the sphere as well. So to be more concrete, this is what the action look like, or rather the Lagrangian. So we have the gravitational part. We have some kinetic terms for the matrix M and for the gauge fields, and then for the scalar chi. Then we have some Chern-Simons interaction here. Here we see that the scalars actually source the gauge fields. And then we have a potential for the scalars. And the potential is given by this formula. So it's a bit of an ugly theory, but it's still manageable. So we want to understand this theory, and the way to do this is to understand first the vacuum of the theory and then the excitations. The vacuum is simply empty global ADS3. And in terms of the coordinates and the fields of the theory, it's expressed like this. So the metric is given by the standard ADS metric. The scalars chi are 0. There's no B field. The matrix M is the identity because the sphere is not deformed. And the gauge fields are 0. For the following, I will use, instead of the standard tau rho sigma coordinates, I will use different coordinates that will make easier to make computations later. So we will define this compact radius psi that lives between 0 and 1, and also this null coordinate psi. And if we rewrite the metric in those coordinates, it looks like this. So there's a conformally flat part and then a vibration on time. Now we want to understand the excitations in this theory. And we're going to look at the normalizable perturbations. To find them, we linearize the equations of motion. And we look for the separable solutions that are regular and that have the correct follow at infinity. And we can find several classes of such perturbations. I'm going to focus on 2 of them, the ones we've called the alpha 1 and beta 1 class. And as you can see, they correspond to in the CFT, they correspond to the states that I was talking about before. those states here. And so they look like this. So in the alpha-1 class, we excite the scalar chi. So we have a B field. And the excitation looks like this. And for the beta-1 class, we excite the shape modes of the sphere. In both cases, if we put the integer m to 0, we get a supersymmetric excitation. And if we backreact this one, we get the exact standard superstratum. Here, if we backreact it, we also get a superstratum, but a new kind that was not known before in the CSD theory. Now we want to understand the backreaction of those states when m is positive, and in particular, we'll focus on m equals 1. And to do that, we need to build an ansatz for our fields. And we will use a U1 squared ansatz. That is to say that we'll impose an invariance under a certain U1 gauge group, the one that rotates the indices 3 and 4. And that means in particular that the scalars K3 plus K4 will be 0. The matrix M will have 0 in the diagonal, and in the 3-4 parts, it will be proportional to the identity, to be invariant. And the gauge fields, the only two non-zero gauge fields are those two here, in the 1, 2, and 3, 4 directions. And then we introduce the fields that for the fields that are non-zero, we define new functions that will be the parameters that we want to. There will be the fields that we need to figure out later. So here for K1 plus K2, we introduce psi dependence. We fix the psi dependence with the mode number n. And in the matrix M, we fix also the mode dependence with mode 2n, so that it's compatible with the equations of motion. And the remaining fields are this new, where we I've extracted this factor square root of 1 minus I squared for convenience. And then there's these scalars mu1, mu2, lambda. We have four gauge fields, and then the space-time metric is like this. So if you remember how I showed when I showed what the ADS metric was in these coordinates, it corresponds to omega 1 equals 1, k equals to xi squared, and omega 0 equals 1.
Is
yes.
omega 0, is that a typo? Should it be time dependent as well? Or?
Sorry?
Is omega 0 time dependent?
Yes, sorry, it should be time dependent as well. Yeah, for now we allow complete time dependence and complete dependence on the radius. And we will see what we can do later with that. So now let me recap what we have so far. So we have a theory in 3 dimensions, n equals 8 gauge supergravity. And in the ansatz that we've built, we have those fields. We have 4 scalars. Nu and lambda are complex scalars. Mu1 and mu2 are real. 4 gauge fields and symmetric functions. And then we have some perturbations that we want to backreact. Those are the 2 perturbations that appear in the fields nu and lambda. And they depend on 2 integers, m and m prime, and those frequencies. Now the goal is to compute the backreaction. So if you have questions so far. Good, so now let's focus on time-independent solutions. To have time-independent solutions, the first thing to do is to focus on a single frequency. If we have several frequencies, it will not be time-independent. And also, we will need to have omega equals omega prime. And the reason for this is that we can build a Q-ball-like ansatz, where we fix the time dependence of the scalars nu and lambda in this precise way, where the frequency of lambda is exactly twice the one that appear in nu. And if we do that, and we fix all the other fields to depend only on the radius and not on time, it turns out that it is completely compatible with the equations of motion. This is comes directly from group theory. And what is nice about this is that now we only have to deal with ordinary differential equations. Everything depends only on the radius. So there are two methods to build the backreaction of those perturbations. Unfortunately, we cannot so far do it analytically, so we will use either perturbation theory or numerics. Using perturbation, yes?
How looks the differential equation? How looks it like?
I don't have them on the slides here. So you can imagine you have 11 equations. The equations for nu and lambda are decoupled. For mu1 and mu2, they are coupled together. Then the 4 gauge fields are coupled together, and then we can solve the 3 metric functions that are also coupled together. And they are second order differential equations, and they are nonlinear, but we will linearize them using perturbation theory. Does that answer? So we want to solve the equations of motion, and we'll do it perturbatively around the vacuum. So we do not build around an existing superstrata, for example. This is something that we can do, but it's much more complicated, and we can only do it at order 1. Here I'm going to talk about the perturbation around the vacuum. And this computation can be actually carried out to rather high order perturbations. It's if we don't fix the mode number n, we take it to be general, we can go up to 4th order. And if we fix n to be some number like 2 or 3, we can go much higher. It's easy to go to 10th order or even higher. And numerically, we can also solve the equations of motion. We can use, for example, a double shooting method. We interpolate the solution from the origin and infinity, and then we use matching condition in the bulk. Or we can use Newton-Raphson iterations. And what we see is that it's possible to actually solve the equations of motion up to a precision of 10 to the minus 50. So it works really well. And here I also want to mention that I've focused my talk on the U1 squared truncation, but those methods can be used more generally. And some of the results that I'm going to show you are actually more general.
Sorry, for this numerical solution, how do you check that are regular?
Regular?
Smooth? Yes, there is no...
For the double shooting method, we actually impose the smoothness at both boundaries. So we solve iteratively in a grid starting from the boundary, and we have expanded all the fields at the boundaries so that they are smooth. So the only variables that we can tune are chosen so that everything stays smooth by construction. And for the Newton-Raphson iterations, I'm not sure how it works. This is what Bogdan has done. And I know that there are some ways to fix the conditions of the boundary, but I couldn't say right now how it works. So this is the sort of results that we get. Those are all the fields of the theory. The first 4 are the scalars. Here, those 4 are the gauge fields, and those 4 are the metric fields. So there's not much to say about the results by themselves, but what's important to see is that in red we have the perturbative results, and in blue we have the numerics. And you can see that they match very well. We are still close enough here to the perturbative regime, but for the numerics we can of course go much further. Here is a plot that shows that the numerics actually work. This is the error. We plot the error on the equations of motion compared to the number of grid points. And you see that starting at 200 grid points, we have a precision that is better than 10 to the minus 50. Now we can look at what the solutions look like far from the perturbative regime, when we are close to the black hole regime. And this is a plot of the size of the circle of the ADS3 as a function of the radius. So if you imagine that you have a long throat, the circle must stabilize along the throat. You get an ADS2 times S1. And when you're close to the origin, the circle must shrink to have a smooth cap. And this is what we see here. So close to the origin, we have a smooth cap. Here we start to see a plateau that corresponds to the ADS2 region. And then the size of the Y circle increases again, and this is the ADS3 asymptotics. So this is an indirect measurement of the redshift. And here I should say that these figures are done for another class of solutions. I've presented the alpha 1 and beta 1. Here this is a different class that corresponds to beta 1 equals beta 2. Beta 2 is a slightly different perturbation, but it doesn't really matter. The results are the same. So what can we learn about those solutions? one of the things that we learn is that there is a frequency shift. We can compute this shift using holography, and it looks like this. So at first order we have the integer mode that we've chosen, and then at higher orders we have corrections that depend on the amplitude of the frequency of the perturbation, and it also depends on the mode number that we choose. This frequency shift in the CRT, we can interpret it as a binding energy between pairs of non-BPS strands, and what we are really interested about is the energy that depends on this frequency shift. But before coming to that, I want to say that we can also compute those shifts numerically, and this is what we get. So the linear part here, so here you can imagine that this is the strength of the perturbation, and here this is the shift in the frequency. The linear part corresponds to what we can see perturbatively, but we can go much further in using numerics, and you see that when the perturbation is strong enough, we start to see deviation, and it all converges to this -1, which we believe, well, it means that the frequency is over the 1 compared to the frequency shift is over the 1 compared to the frequency itself, and this is also a sign of the fact that the redshift is very high. So now let's look at the energy of those solutions. That it can be also computed using holography, and it takes this form perturbatively. The first order correction is actually the shift in the frequency that validates the hypothesis that this corresponds to binding energy between non-BPS strands. And what we expect to see from this energy is that while supersymmetric states have very neat way, the energies of the supersymmetric states are distributed in this very ordered way with a large gap and a large degeneracy. What we expect from non-supersymmetric solutions is that the degeneracy should be almost entirely lifted, and the energy gap should be much smaller over the exponential minus the entropy. And here what we see is that, yes?
Sorry, in this cartoon plot, should the supersymmetric state be at the bottom?
This is the conformal dimension of the states.
Yeah. So where is the BPS state? They do not.
They're all BPS in this cartoon.
But wouldn't some states remain BPS?
Sorry?
Wouldn't some states remain BPS? Even as strong coupling. I know you the form.
I'm not saying that those states are the same as those ones. This is just a cartoon to say supersymmetric states are distributed in that way, and non-supersymmetric states should be distributed that way.
Not necessarily. I think the gap will be there. You have a gap for the non-supersymmetric.
Yeah, but
so whatever stuff begins above.
I'm not saying that this is near supersymmetric or that. I mean, this is a random part of the spectrum. It's not.
Okay. If you look in the middle.
Okay, so that answers my question.
Okay. Here, what we see is that the shift in the energy actually depends on the amplitude of the perturbation. It depends on the type of the perturbation. It depends on the mode numbers. So we have much more for all those states which would have the same energy here. Actually, the degeneracy is lifted, and we can actually plot what the spectrum looks like for those states. So here I fix the large n, the n of the CFT to 1000. I fix the momentum to 50, and I look at all the states which have this momentum. Here in red, it corresponds to the energy before the zeroth order energy before computing the back reaction. So if you want, it's the energy of the CFT states at the orbifold point, and in blue, it corresponds to the energy in the supergravity regime. What we can actually compute using this formula here and these corrections. And as you can see, that all those red lines here that actually have some degeneracy, they are all lifted, and the states, the energy level look more or less random. It starts to have very small gaps. Of course, we can't do any sort of we can't analyze the statistics of those states. We don't have nearly enough states, and they are not randomly picked or anything like that. So it's not like we can say whether it's a random matrix, statistics, or something else. But it seems like it's already a sign that we're getting somewhere, and we are getting to a spectrum that looks chaotic. Now I want to talk about time dependence. Yes.
Just one more question. Can you do the same for the states that would become near BPS at strong coupling?
So what we have is we start with a perturbation that is already non-BPS.
Yes.
I mean, the perturbation looks like where was it? It looks like this. So
no, I understand, but you could pick M very small, right? The first M equal 1.
Yes.
And
Yes,
then
we
trace
do
what
take
happens
M
to
equals
those
1.
states. So my question is, would the gap between the BPS and first near BPS state, does it seem to close or does it seem to stay open?
I don't know about that. This one?
The first one that doesn't drop as much as the rest, is that M is 1 or is that
It's n equals 1/2. It's a bit of a particular case. There are
I'm
some
wondering
problems with the
whether
numeric.
I know we always wondered about that, but I'm wondering whether that might be something along the lines of what Luke is pointing to, that one doesn't drop as much as the rest.
I don't know if it's connected. I mean,
Just a thought, anyway.
yeah, okay, so let me switch to time-dependent solutions. Why do we want to consider time-dependent solutions? Mainly for 2 reasons. The first one is we want to build larger families of microstates. And to do that, well, within the consistent communication, there is not much else we can do. And in particular, if we can build more states, it means that we can populate more this kind of graphs. And the second reason is that we want to study the dynamics of microstrata. And perhaps we can learn some things from this study in IDS3 to prepare for flat asymptotics. We know that the non-supersymmetric solutions will have to decay in flat asymptotics, so we need time dependence. And so let's look at what we can do within this model and in the IDS3. So now we come back to all our fields and we reintroduce all the time dependence in all the fields. And we have many more possibilities for which perturbation we want to look at. So we have to choose something. Right here we can do any kind of combination we want. We have a sum compared to before. So the first thing that I want to understand in this system is related to the frequency shift that I was talking about. In the time-independent solutions, what we've done is that we first started at 0th order by fixing all, the frequency of the 2 scalars to be equal, or rather, omega equals omega prime signifies that the frequency of the lambda scalar is twice the frequency of the new scalar. And then we've computed the corrections to these frequencies at each order, and we have the first order corrections. But a priori, there's absolutely no reason why the corrections of the frequency omega should be the same as the correction to the omega prime. And in fact, if the delta omega is not delta omega prime, we would break the Q-bord ansatz. And that means that the solution cannot be described using a time-independent ansatz. And this is what we see, actually. Because if we try to impose, to have both perturbations at the same time within the Q-bord ansatz, using the time-independent ansatz, what we see is that generically we develop log singularities in the perturbative expansion. And what we have found, and what the results that I've shown you represent, actually correspond to very precise relation between the amplitudes of the 2 perturbations. So you have to actually tune the perturbation in the lambda scalar to be exactly -1/4 alpha 1 squared, so quadratically to the amplitude of the other. Otherwise, the solution is not defined and you get log singularities. Rodolfo talked about the special locus. This relation is called the special locus, and Rodolfo talked about it in the supersymmetric context. But in the non-supersymmetric context, we also find the special locus, and you can sort of understand its meaning both in the bulk and the CFT. But the question that I want to ask now is, now I have a time-dependent ansatz, and I want to know if we can break away from the special locus. Why this problem is particular? If I were to take other perturbations, for example, say a perturbation with m equals 1 and a perturbation at m equals 3 at the same time, I would have an explicit time dependence already at first order, and I will already have to excite more and more modes starting at second order. Here, with this system, if I focus on the special locus, actually at first order I take only m equals m prime equals 1. So at first order there is no explicit time dependence, and at second order we see that there is no time dependence either. Actually, those log divergence that I was talking about only appear at third order in perturbation theory. That means that the perturbation theory stays simple at least up to third order. So that's a nice starting point to understand time dependence theories. All right, so let's talk about a bit how to do the perturbation theory. We expand all the fields in the powers of a parameter epsilon, bookkeeping parameter. At first order, we fix the fields nu and lambda to have those values. So I take the frequency to be 3 at first order and 6 for lambda. And the perturbations look like this. Now I go to second order, and as I was saying, this is still very simple. There is no explicit time dependence beside the exponential 3it and exponential 6it here. This is only for the 4 scalars, but it works exactly the same way for the gauge fields and for the metric functions. And so everything here is still simple. Now I go to third order, and this is what I get. I get first a first term that is still in power of exponential, still multiplying exponential 3it, and it's a simple polynomial link psi. So everything is good for this term. But then I also get this term. And here I have the time that appears here, and that means that this term grows unboundedly with time. At higher orders, it's even worse, because if I go to order 2k plus 1 or 2k plus 2, the time dependence becomes t to the k. So it grows even quicker, and the perturbation theory is invalid even quicker. Because when we do a perturbation theory, the general rule to understand the validity of the theory is that at each order, each term is smaller than the previous one. And here it's not the case when t is large. These kind of terms, we call them secular terms. And there are terms that grow unboundedly with time, and that invalidate the perturbation theory at large times. And in general, their presence is due to resonances in the spectrum. In particular, there are staples of perturbation theory in ADS3. And this paper here originally studied them. And in this paper in particular, they have been shown to be associated with instabilities in the theory, in the perturbation. And all perturbations who have terms like this that cannot be resummed actually are fall into a black hole. But this is exactly the point. Sometimes it is possible to resum those terms, and this is what I'll be trying to do now. And something that we can already notice is those blue terms here that multiply the secular terms. If maybe you recognize them, they correspond exactly to the first order perturbation here. And that's a sign that we'll be able to reabsorb them by a frequency shift. If we shift the frequency by a small amount here, at third order it will correspond to something like this. So let's see how we can do that. We want to resum those terms. And the method that I want to use to resum those terms is called the Poincaré-Lindstedt method. And I will try to give you a small introduction to this method by studying a much simpler equation, namely the anharmonic oscillator. So let's consider an oscillator that looks like this with a small epsilon x cubed term. And we want to solve this equation perturbatively. To do that, we will expand this field x in powers of epsilon. And we have an expansion like this. If we then introduce this expansion back into the equation and we solve order by order, this is the kind of result that we get. At first order, we get a simple cosine. And then when we get to order 1, already we see the appearance of this secular term. This means that this perturbation theory will not work and will break down when t is over 1 over epsilon. But we can do better, and we can use Poincaré-Lindstedt to do better. Now let's say that instead of the naive perturbation theory, we will also expand the frequency in power of epsilon. And to do that, we define this new time parameter t, big T, which is proportional to the time little t with a frequency that is expanded in powers of epsilon. Now, the field x, I redefine it to be a function of big T in such a way. I reintroduce this into the equation, the original equation, and I solve order by order. And what we see, at first order, we still have the same cosine, but at second order, we have this secular term that is multiplied by this factor here. And this factor can be put to 0, can be cancelled if we choose the frequency shift omega 1 to be 3/8. And if we do that, and we then translate back into the original variables, in the original variable t, the result looks like this. And this is the lesson here. And the lesson is that when we have secular terms that appear at some point in the perturbation theory, we can reabsorb them in a frequency shift of at a lower order. So here we had before we had a frequency of equal to 1, and now we have at 0th order we have a frequency equals to 1 plus 3 epsilon over 8. So we want to do the same thing with the solution that I was presenting before. In our gravity solution, we have two scalars, and they have 2 frequencies. So I'm going to introduce 2 new times, t1 and t2. This time t1 will correspond to the frequency of the scalar nu, and this time t2 will correspond to the frequency of the scalar lambda. Now I look at the normalizable excitations in terms of those 2 new times, and they look like this. So this is exactly the same as before, with an exponential it1 and here an exponential it2 instead of the previous frequencies. But there's also a subtlety here that for any integer k, since 2t1 is equal to t2 at first order, at 0th order, when epsilon equals 0, then I can add this term in the exponential in the normalizable excitations, and it's still a solution of the equation of the linearized equation of motion. So at first order, I can make a choice. I can simply say k equals k prime equals 0. I want to study these perturbations. I will also fix n equals 2 for simplicity. But at higher orders, it's more of a problem, right? Because at order 2, for example, I could introduce a correction, an amplitude correction for any value of k, and there's nothing that tells me that those terms would not be here. So here I will make a choice. I will say that if a term with a k non-zero appears in the right-hand side of the linearized equations, I will introduce a correction to the frequency at this order. And if it doesn't appear, if such a term does not appear in the right-hand side, I will not add the corrections. I can't deal with an infinite number of corrections. So at first order, this is what it looks like. And you see that I have a term in exponential t2 minus t1, which corresponds to k equals -1. And so now I will introduce a constant that will allow for corrections of the amplitude. Same for lambda, at second order, I have this C2 here. And all the other fields work the same way. Now I go to third order. This is the order where we had the secular terms. And I look at what I get this time. And in front of the secular term, I get this term here. And this is exactly what we've seen before in the with the anharmonic oscillator. If I choose the frequency shift omega 1 so that this term is 0, I can completely reabsorb the secular term into a frequency shift. And it works exactly the same way for the scalar lambda. And I get those 2 frequency shifts here, omega 1 and omega prime 1. Those frequency, there's a bit of a subtlety here that I've not mentioned so far. Those frequency are not exactly physical by themselves because there's a gauge invariance in the theory that rotates the frequency. And actually, there's a way to make them physical by going to the by going to the CFT and using holography to compute the correct frequency. This is what we've done in the time-independent solutions. Here, I don't know what the CFT dual would look like. So those frequencies are not exactly physical, but there's something that's physical, and it's the difference between those two frequencies. And so what we notice is that those two frequencies are not equal. Their difference is different from 0. And that means that's a confirmation that the solution is genuinely time-dependent, sorry. And indeed, we can break away from the spatial locus using this method. Also, I want to point out that at third order in the lambda scalar, we have a frequency of order 3t2. So it corresponds to 18t when we come back to the original t variable. And you see that we start to populate higher frequencies. There's a non-zero term in front of this frequency. Now, what happens at fourth order? At fourth order, it's much more subtle. It's much more difficult. We have this, in the solution for nu, we have this frequency here, 3t1 minus t2. And when we try to write it without secular terms, we get log divergences as before, but we get two log divergences. And in fact, if we want to correct them, we can correct one of them because both those terms, 1 and 2, have some factor of the frequency shift in it. But if I try to fix omega 2 such that 1 is 0, then 2 will be non-zero, and conversely. That means that this log singularity, it cannot be cured with the frequency shift. Instead, if we want to have a regular solution, we can come back and reintroduce a secular term, but that's what we are trying to avoid. So in other words, secular terms cannot be resolved at order 4, at least using the Poincaré-Lindstedt method. Now, what does this all mean? What explains this failure to resolve the secular term? And here there are essentially two possibilities, and I don't have the answer, so if someone wants to try to solve this problem using numerics or CFT, I will be very happy to learn about the solution, but there are two possibilities. The first one is that the Poincaré-Lindstedt method actually is not powerful enough to resum the secular term at order 4. There are other methods, such as the multiscale method, but this method is not really used so much in all the papers that study ADS3 instabilities. The reason is that there is not so much mathematical grounds for the method. And in fact, I tried to use it, and at fourth order, we get equations that are very complicated, and I don't know how to solve, or even if they have a solution. And in general, as I said, people do not use the method, and in ADS3, it's the failure of the Poincaré-Lindstedt method that corresponds to instability towards the black hole. So the second possibility, which is maybe more likely, is that the failure of resummation corresponds to an instability of the solution. But now the question is towards what? For example, we could say that maybe the instability leads to the formation of a black hole at long time. This, in the context of the microstate geometry program, we want to interpret it as saying that the three-dimensional theory does not have the degrees of freedom to resolve the black hole and the instability. And so maybe if we go to higher dimensions, or maybe if we include stringy degrees of freedom, we would get something else. But that means that we would not be able to see anything new. So this would be a bit of a failure. And the second possibility is that after the solution is unstable and converges to a fine-tuned time-independent microstrata, say the spatial locus microstrata. Perhaps the spatial locus acts like an attractor, and these solutions will naturally converge to it. Another solution is that we converge to something else entirely. Maybe there is a more complex microstate, as I was saying, in 6 dimensions or so on. And the last possibility is that we have an eternally oscillating solution. Now, which one of those 4 possibilities are actually the correct one? I have no idea. I'd like to see numerics or try numerics or maybe some CFT arguments to understand which one is the correct one. So let me conclude. I've shown you, I think, I've shown you that we can derive perturbatively and numerically solution microstate geometries that are non-supersymmetric. They are dual to non-BPS states that look like this. So they are the heavy states that Rodolfo was talking about that correspond to the light state excitations. We can use holography to compute the total energy of those states at strong coupling. We see that the spectrum. We see that in the spectrum the degeneracies are lifted and it sort of looks like a chaotic spectrum, but without any proof that it is exactly this. But yeah, the frequency shift depends on the amplitudes and on all the mode numbers. So this is a good sign that it will actually be chaotic. And then, as I've said, there is a much richer phase space that is attainable with time-dependent solutions. But there is always the question of the stability, and it's unclear so far if those solutions are stable or not. So what I would really like to understand is the long-term destiny, the stability of those time-dependent solutions. And I was saying, I would hope that using numerical method it will be possible. I'd like also to maybe explore more the phase space. As I was saying, the trying to break away from the spatial locus was the simplest thing we can do, but a priori there's a very large phase space that we can explore and try to maybe populate more the spectrum. I'd like also, there's a specificity in ADS perturbation theory that if one picks at linear order very specific combinations of modes that decrease as a power law with a mode number, there's a possibility that those specific perturbations do not develop secular terms. Generic perturbation develops secular terms, but one can fine-tune perturbations that do not develop secular terms. And it will be interesting to see if there's a similar behavior with microstrata. Then also, I would also want to understand better the holographic dictionary of microstrata. I haven't talked too much about it, but so far, what we can match with microstrata between the CFT and the bulk is essentially 3 parameters. We can match the 2 angular momenta and the momentum h minus h bar. Because we don't have any protected quantity anymore. We can only match the integer quantities. So it would be nice to try to understand more of what happens to the other quantities. And finally, the big thing would be to connect microstrata to flat asymptotics. We know that the solution will decay. We want to understand their time dependence. We want to understand how to connect them to flat space smoothly. And the huge goal would be to have an equivalent of the Hawking radiation. Thank you.
Questions or comments?
So there was a similar sounding issue for superstrata, multimode superstrata, where it turned out that to get rid of various singularities in the linear system, you had to enlarge the set of modes that you needed to include in the ansatz to supercharged modes and et cetera. I mean, they have various names. So it sounds like here you're trying to find a solution within some restricted ansatz for the set of perturbations that you allow.
Well, at this point, the ansatz is almost fully general within 3 dimensions. I fix completely the dependence in the circle of ADS. I fix the mode to be n, and given to be, for example, 2.
I guess what I'm wondering is when you find these secular terms, could it just mean that you need to incorporate more degrees of freedom in order to find more things that you can adjust in order to cancel the secular terms?
Well, I don't know, but I would say no, because those secular terms are exactly the ones that appear in the perturbation theory of ADS. And there have been a lot of studies of degrees of freedom like this, of theories like this, and they always found that secular terms and instabilities are really completely generic in ADS. So I would say that This is a symptom of ADS rather than a symptom of the theory, the specific theory that.
But this perturbation is blowing up somewhere, or just everywhere at some time?
Yeah, so you see this is the dependence in the radius. So it's sort of a bump. It's
like, is it sitting at the supertube?
Yeah, it looks kind of like this, the new scalar, and it's multiplied by square root of 1 minus psi squared. So actually, it's when you include the square root dependence, it goes to 0 here, and it's a bump, and the bump is located at the superstrata model.
Okay, that sounds like it wants to deform the supertube in some way. It's like that shock wave that David was talking about earlier today.
Well, I'm really starting the perturbation theory from the vacuum here, so the result is different from the superstrata. We can deform the superstrata, but here it's really a deformation of the vacuum.
Just iteration on the same argument. You start off at first order just turning on two modes, right?
Yeah.
But to paraphrase what Emil's saying, can you go back to the beginning at order 4 and say, okay, I forgot to turn on some other modes at 0th order, but they should be down by epsilon to the 4th in some sense?
Well, yeah, that's what I was mentioning in the conclusion, that we can, in ADS, there are ways to choose those alpha m that have a power law fall off, right, in such a way that the circular terms disappear. But it's a really fine-tuned way of choosing the.
But we've seen that kind of thing before in superstrata. I think the comment I make is that this is the kind of thing, if we could get a numerics of this, we could actually see what the new idea is, the new ingredient is to complete the perturbation theory.
Mm-hmm.
That's very nice.
Yeah, maybe just as a comment. First of all, thanks for your really nice talk. That was really intriguing. And talking about the numerics, I think my suggestion would be to go back to the Bizon-Rostorowski paper that you're citing here. And they actually do time evolution in effectively 1 + 1 using the symmetries of the space-time. And this is where they found an instability for ADS leading to black hole formation. So one thing that could be interesting to see if with your field content you find something similar, or whether you find these oscillating solutions. And I think we should talk about this maybe offline, but yeah. Yeah, okay.
My hazy memory of your talk, I think you said some remark that when you couple to flat space, it can actually stabilize the instabilities of ADS. Is that true or not? There's some way that the leakage out can actually stop ADS. So if you have something that's asymptotic ADS for a bit and then goes to flat space and then can dump energy into the flat space, can that stabilize the instabilities of ADS?
Maybe. I actually don't know.
Okay, because the same thing's going on here. If it can leak enough radiation out in Hawking radiation and it's starting to run away, maybe it can stabilize it. Anyway.
I mean, I think one of the things that leads to this instability. Okay. So one of these things that I think leads to this instability in ADS is exactly having this time-like boundary, which acts like a mirror and can focus your modes. So yes, it's definitely something we should think about. And I think there's a lot of mass and numerics literature from about 10 years ago. Yeah, so good.
Okay. Any other questions or comments? If not, we thank Anthony again.